Okay. An example of a surface of revolution is the general torus. Example. It's called the general torus. Its parametrization is given by alpha u. It's a surface of revolution. This is a circle of radius 1, and you rotate this. It's in the xy plane. You rotate this about the x-axis, and you get what? Okay, let me write r plus little r cos u cos v, r plus little r cos u sine v, and then the last coordinate is just r times sine u. Here note that x of u plus u, yeah, okay, u plus 2 pi v is just x uv, so that x is not 1-to-1. So what is this gadget? Let me just draw what's happening. Now, this thing, so the x coordinate is just r times cosine u, and this is just sine u. If I didn't have this, it would be just circle, right? Cosine u, sine u. But this is just a little bit shifted circle. So here is r, and this thing is just the circle of radius 1. Okay. So this is r alpha. And we rotate this about which axis then? About the y-axis, not x but y-axis. So yeah, I will rotate this about the y-axis. So this is x and this is y. If you rotate about the y-axis, this is what you get. Okay. So y coordinate. No. Bir dakika. X'i r plus cos. Bunu ne yapıyoruz? About the y-axis, right? Yeah, okay. Yeah, okay. So this is the z coordinate, and we rotate about the y-axis. And what is the picture you will get? Your surface will be like this. So this is the torus. Okay, it's not a nice torus. Okay, so you will get something like this. Okay. Yeah, so this is the z-axis, this is the x-axis, and this is the y-axis. And this circle is this circle here. Okay. We just take this circle and rotate about the y-axis. And this is the parametrization. Küçük R şu. Yeah, here if I take R units, little r, so okay, make this R. Yeah. So R is a positive number, little r is also a positive number, and they correspond to R is this radius, and big R is which radius? It is the one yeah, you're right. Big R is this. Okay. Yeah, so R is this distance, little r is this one. Okay. Parametrizations are good because they provide a global formula for surface patches at any point. Okay, you have the same function for a surface patch. You just need to choose your domain appropriately so that the function x is 1-to-1. Okay, that's it. And homeomorphism onto its image. All right, so what else? Okay, so we have so-called ruled surfaces. This is another type of surface, okay? A ruled surface is a surface swept out by a straight line L moving along a curve beta. Okay. The various positions of the lines generating the surface are called rulings. Okay. Such a surface has parametrization, has a ruled parametrization. I will explain what does this mean. So here is parametrization UV. So beta U plus V times delta U. Here beta U is called the base curve. And delta U is the direction curve. So let me explain what is this. So suppose we have our curve beta. This is the point, let's say beta U. And we have a ruling. What do we mean by that? At each point of the curve, I have a direction vector, okay? At each point of the curve, I have a direction vector like this, you know, and then like this. These curves may change, okay? These vectors may change. For example, it can be like this. And then and at any point, let's say, so our in the UV plane, I have this UV. If you choose such a line segment, what will be the image of this? What will be the image of this? At a fixed, let's say, U0. So U0, this point is, let's say, beta U0. And this is, this vector is just delta U0. At this point, I have this vector. And as you move on this, what you do, you change. So here, let's say you have U0, U0, U0. As you move, as you change V, this is fixed, this is fixed, you are changing V. So it means you are at this point, and as V changes, you just move along this vector. In other words, you move on this line, okay? On this line. So at each point of your curve, you have a line in the direction of this vector, okay? So this surface is something like this, you know, a part of this surface. You have, you know, this curve, and then you have just lines on attached to this surface. Bu sizin surface'ınızın içinde bir eğri, yani surface burada şey gibi, bu eğrinin etrafında dönen doğrular gibi. O şeylerin seçimi, şunun seçimi, the choice of this is up to you. You choose them any way you want. So that this thing is, of course, a parametrization. Okay. And this is its description. Yes. Yes, yes, yes. Lines are attached to this curve. You have a curve in the space, and to each point of that space, you attach a line. Okay. Of course, there will be some rules of attaching those lines so that the resulting object is a surface. Okay. Now we will see that. We will write down basically the condition which makes this expression a parametrization, meaning that the derivative is 1-to-1. Yes, yes, yes. Yeah. So this is a ruled surface. Plane is a ruled surface. And when you rotate this, of course, you cannot rotate this, but if it is, yeah, so you understand what. Now let's see. Okay, let me change the board. So x up uv is just beta u plus v times delta u, right? These are vector valued functions, right? At each point, this is a vector, so that it's, it defines our curve. And to each point, I attached another, vector. So let's see, what is x up u? Well, it is just beta prime u plus v times delta prime u. And x sub v is just, this is 0. This is just 1. So this is just delta u. Okay. These are just two vectors. So what is x sub u cross x sub v? So it is just delta u, sorry, beta prime u plus v times delta u cross delta u. Okay. Yeah, okay, let's. So this expression shouldn't be 0, okay? This expression shouldn't be 0. So this shouldn't be 0. I mean the 0 vector, of course. This is a vector, right? This is a vector. This is another vector for all UV. Okay. In some interval cross R. Okay. Well, we may choose this also, maybe. Okay. Kalsın böyle kalsın. Okay. Yani illa sonsuza kadar gitmesine de gerek yok bu doğruların, right? In general, you may choose this piece something smaller than R, an interval, so that your surface. So suppose your surface is like this. So this is your beta. Beta u, and at each point you have this ruling, okay? Right? It's just going like this. and this is just delta u. This vector is delta u. You multiply this with some number and add to this, so you just obtain a point on this line. Okay, and this is a part of your surface. Okay, so this puts some condition on delta and beta, of course. Okay, so they cannot be just arbitrary, but still you have a lot of freedom, I guess. Okay. So for XUV to be as parametrization, X of U cross X of V shouldn't be 0, 0, 0, right? Here is one example of a ruled surface. Consider the cone. Cone given by Z squared equals X squared plus Y squared. This is a ruled surface. Ruled surface. This is how it looks like. What are the lines? Lines are just lines through the origin on this cone, right? These are the lines, right? How can you, for example, give a parametrization like this for this? You can do the following. You may choose your beta, for example, as this curve, okay? A curve which is in the basically XY plane. So maybe not XY plane, but above the XY plane like this, beta. And you may choose your vectors, delta U, as these vectors. Okay. So this point is just beta U, and this vector is just delta U, and beta U plus V times delta U is what? You just move on this line as you change V, okay? So this is a ruling. Yani XY düzleminin üzerinde ona paralel bir tane çember alıyorsunuz. You take a circle parallel to the XY plane, above the XY plane, and to each point of this, you attach the vector actually joining this point to the origin, okay? You may choose this delta to be the vector joining this point to the origin, and then you just let U and V vary. We may maybe do this. So one may choose beta U what? This is, let's say, a circle of radius 1. You see, when Z equals 1, this is X squared plus Y squared equals 1. So it is the unit circle, right? So I may choose this to be just cosine u, sine u, and then the z coordinate is 1. And then what is the vector delta v? Delta v is the vector joining this point to the origin. Okay, joining this point to the origin. So it is just minus the vector joining origin to this point. What are the coordinates of this point? Well, they are just this. So delta u is just minus beta u. Yok. Yani v'yi eksiği alırsın. Ben bu şekilde tarif ettiğim için öyle aldım. So my x uv then is just beta u plus v times delta v. So delta u. So this is just what? 1 minus v times beta u. Okay. And for this to be a surface patch, I guess, so, you know, this point is the problematic point, right? This point is not a point which you want on a surface, right? So you should avoid this. It means that v shouldn't be 1, okay? V shouldn't be 1. So I guess I may choose u to be the whole real line, right? Whole real line. So you just move around this curve as many times as you want, doesn't matter. It doesn't have to be 1-to-1. But for the v coordinate, you have to be careful. You don't want v to be what? You don't want v to be 1. So it is okay, r minus 1. Sorry? Okay, at that point, you are at the origin, and this is not a point on a regular surface. Well, you may check that, you know, your function won't be bakabiliriz aslında. Okay, let's see. Okay, orayı kullandık zaten. So what is x sub uv? X sub uv is just 1 minus v times beta u. Beta u is just cosine u, sine u, and 1. Okay, and 1. So this is the expression then. So it is 1 minus v times cosine u, 1 minus v times sine u, and 1 minus v. Okay, what is x sub u? Derivative with respect to u is just 1 minus v, well, with a minus sign, sine u, 1 minus v cosine u, and 0. Yes. And what is x sub v? Well, it is minus cosine u minus sine u and minus 1. So what is x sub u cross x sub v? Okay, let's write down. Şimdi şu ikisini çarpacağız, değil mi? Neyse şöyle yapayım da. U1, U2, U3. Evet. Burası V eksi 1 çarpı sinüs U 1 minus V times cosine U and 0. And here minus cosine U minus sine U and minus 1. So this is just okay, V minus 1 times cosine U, and then okay, bunu çarpıyoruz. 1 minus V, ama bir daha şey yapacağız. V minus'tan sine U, and then this plus this. So this is sine squared and then cosine squared. Okay, so it is just 1 minus V, I guess. So you see, this is not 0 exactly if V is not 0, right? So this is not 0, 0 if V is not 1. Okay, so at 1, this is not a parametrization, and there is a good reason for that, because at this point your surface is not actually a surface in the proper sense. Tamam mı? Problem şu, the problem here is that at this point the cone doesn't have well, a tangent plane. Actually, it has tangent vectors, but they don't form a plane, right? They form so-called a cone, okay, at this point. So you don't have a tangent plane. But our definition of surface requires that at each point you have a tangent plane, because the derivative map of the surface patch is 1-to-1. So it maps the tangent plane of the domain to R3 in an injective map, in an injective way, so that it takes your tangent plane in the UV plane to R3. Yani sizin parametrization aldığımız zaman, şimdi bu UV plane in the UV plane, you have this tangent plane at this point, right? You have tangent vectors. If this is a surface patch, the derivative is 1-to-1, meaning that these two vectors are mapped to two linearly independent vectors like this, so that they span a tangent space. But here you don't have a tangent space. Okay. So Another example of a ruled surface is the surface defined by z squared x squared plus y squared minus 1. Okay, it is this surface here. So this is something like this. What are the rulings? Well, as your curve beta, you may choose this circle again, beta, u to be just, again, when z is zero, so this is the circle, when z is zero, so it is the circle in the xy plane, and when z is zero, this is just the unit circle. So this is just, again, cosine u, sine u, 0. What about the rulings? At each point, I should give you a line, right? So that it lies on the surface. How can we find those lines? Well, here is how can we find it. You see, on this gadget, so okay, okay, so for any c in this interval minus 1 1, the lines okay, z equals x minus d, y is plus minus c, and z equals z plus d, y equals plus minus c, where d is just 1 minus c squared, c is chosen to be like this, are contained in the surface. So we have two rulings actually. One set of lines are like this. So y equals c and z equals x minus d. So this is a surface actually, not surface, plane in the xyz space, in 3 space. This is a plane. This is another plane, and the intersection of these two planes is a line. So it's a line like this, you know, something like this. And this one is, so one of them is like this, the other one is like this. How can you get these expressions? Well, you just, manipulate this. So you let y equals c. When y is c, let's see what we get. Z squared is equal to x squared plus c squared minus 1. So this is z minus x squared. This is just d squared. D is just, okay, yes. D squared is 1 minus c squared. Bir dakika. Şöyle mi yapsam? Okay. Bir okay, this is not correct. I should write it this way: 1 minus c squared x squared minus z squared. Okay, now this is d squared. And then what you do, you may just let x minus z to be d and x plus z to be d. Bir dakika ya. Yok, böyle olmaz da. Şöyle diyeyim. Or burada neyi kastediyorum? Yok, burada bir gariplik oldu. Pardon. Okay, I have to just show you that, you know, these are contained in the equation. I mean, this gadgets satisfy the equation, right? So z squared, is this equal to x squared plus y squared minus 1? So okay, so I let z equals x minus d, so x minus d squared is equal to, is this equal to x squared plus c squared minus 1. So this is just okay. Buradan da ne çıkar? X kare r minus 2xd equals x squared plus c squared minus 1. So these are gone. D squared is just yok, öyle olmuyor. Okay. Well, let me think about this. Okay, next time I'll fix this. I think I wrote something not correct. Well, it should be something easy, but nevertheless, okay. Well, okay, I'll fix it next time. I thought this was okay, but now I realize that it's not actually correct. Ya problem bu y'nin y sabit olamaz tabii, değil mi? Şöyle diyeyim. Okay, let me stop the recording.